Let a and b be positive integers such that a square plus b square is equal to 2023 square. Find all possible values of a and b. You may use the chapters below to jump to the section of thinking process and different parts of the detailed solutions.
Hi there, welcome to my channel Mathenthusiasm. Today I want to share with you this question of 2023. You may want to check out another interesting question of 2023 and trigonometry in the link above. Without further ado, let's get started. First of all, the equation a squared plus b squared equals to 2023 squared. The form looks like the famous Pythagorean theorem. Because a and b are positive integers, the equation belongs to the type of Diophantine equation. We're going to do the prime factorization of 2023. That is, 2023 is written as 7 times 17 times 17. Here, 7 and 17 are the prime factors of 2023. We're going to use this to figure out the first solution. Therefore, a squared plus b squared is equal to 7 times 17 times 17 whole square. Put the square for each number, then it is equal to 7 squared times 17 squared times 17 squared. If we focus on 17 squared at the back, then we might think of a combination from Pythagorean's theorem, which is x squared plus 15 squared is equal to 17 squared. We call the three numbers 8, 15, and 17 Pythagorean triple. We're going to elaborate this idea more in the later part. Now, we put this equation into a squared plus b squared, then it is equal to 7 squared times 17 squared times bracket 8 squared plus 15 squared. Expand the bracket, then we get the sum of two terms. The first one, 7 squared times 17 squared times 8 squared. And the second one, 7 squared times 17 squared times 15 squared. Both of them look like a square. Group the three numbers 7, 17, and 8 together. And we do the same for 7, 17, and 15. Then we get this. Calculate the product in each bracket, then it is equal to 952 square plus 1785 square. Therefore, a and b can be equal to these two numbers. We may also reverse the order to get another pair. Now we obtain two solutions. However, is there any other possible answers? Let's check it out in the next part. The key to solve the problem completely is to make use of Pythagorean triples. In Pythagorean's theorem, a squared plus b squared equals to c squared, there is a general formula for the three numbers a, b, and c. If the three numbers are relatively prime, that is, their highest common factor HCF is equal to 1, then the formula to generate a, b, c is the following. A is equal to m squared minus n squared, b is equal to 2mn, and c is equal to m squared plus n squared, where m and n are positive integers and m is greater than n, to ensure that a equals to m squared minus n squared is positive. This formula is discovered by important Greek mathematician Euclid, written in his most influential geometry book, The Elements, Book 10, Proposition 29. This is called the Euclid's formula. For example, if m is equal to 2 and n equals to 1, from Euclid's formula, we'll have a, b, c equals to 3, 4, 5, which is the well-known and also the smallest Pythagorean triple. We want to verify if this formula satisfies the Pythagorean theorem m squared minus n squared whole square plus 2mn whole square equals to m squared plus n squared whole square. This is a straightforward exercise of expansion and simplification. I'll leave it for you to try. On the other hand, if the HCF of ABC is not 1, say it is k, then Euclid's formula can be modified a little bit. We just have to multiply each term by k. So the generating formula is a equals to k times m squared minus n squared, b equals to 2kmn, and c equals to k times m squared plus n squared. Here, m, n, and k are positive integers, where m is still greater than n. For example, if k is 3, m is 2, and n is 1, using the formula, then a, b, c is equal to 9, 12, and 15 respectively, which still satisfies Pythagoras' theorem. With this powerful tool, we're ready to solve the original question, a squared plus b squared equals to 2023 squared. Let's see the detailed solutions in the next part. Now, we apply the Euclid's formula of Pythagorean triple. So for the given equation, c is equal to 2023, and c is equal to k times m squared plus n squared as well. Therefore, k is a factor of 2023. Let's find out all the values of k. Because 2023 is equal to 7 times 17 squared, then the factors of 2023 are 1, 7, 17, 7 times 17, 17 squared, and 7 times 17 squared, which are the following 6 numbers. By this special way of writing, we can ensure that there's no missing factor. Indeed, there's another useful formula to find out how many factors of an integer are there. Please check out another video on number theory later. We shall also discuss why the way above is important in that video. Let's continue. So k can take these 6 values. Moreover, consider the range of values of n. Because 2023 over k is equal to m squared plus n squared, and m is larger than n, therefore m squared plus n squared is larger than n squared plus n squared. So we have 2n squared on the right. Divide 2 to the other side, we get n squared is smaller than 2023 over 2k. This helps us to further restrict the values of n. Now, we're going to put the 6 values of k into the equation to solve for m and n. We shall start from the largest to the smallest. It is because with larger k, then the value of n is smaller. Using Euclid's formula, we can find the values of a and b. Case 1, if k is equal to 2023, by the equation m squared plus n squared is equal to 2023 over k, then m squared plus n squared is equal to 1. Because m and n are both positive integers, they are larger than or equal to 1. Therefore, m squared plus n squared is larger than or equal to 2, which is larger than 1. Therefore, there is no positive integer solution of m and n. Case 2. If k is 289, then m squared plus n squared is 7. By the range of values of n squared is smaller than 2023 over 2k, then n squared is smaller than 2023 over 2 times 289. This is 3.5, which is smaller than 2 squared. Therefore, n is equal to 1 only. From the equation, we get m is equal to 36. So again, there's no positive integer solution. Case 3. If k is 119, then m squared plus n squared is equal to 17. So n squared is smaller than 2023 over 2 times 119. This is 8.5, which is smaller than 3 squared. So n is equal to 1 or 2. Putting these two values of n into the equation, then we have mn is equal to 4, 1, or square root 13, 2. This solution is rejected as m should be an integer. Therefore, kmn is equal to 119, 4, and 1. Putting these values into the Euclid's formula, then a is equal to k times m squared minus n squared. This is equal to 119 times 4 squared minus 1 squared, which is 1785. B is equal to 2kmn, which is 2 times 119 times 4 times 1, which is 952. There are the solutions that we obtained in the thinking process. At this moment, we've gone through 3 values of k already. and we only got the same answer as in the previous part. Is there any other solution? In the final part, we're going to put the remaining 3 values of k into the equation to solve for m and n, and see if there's any other solution. Case 4. If k is equal to 17, then m squared plus n squared is equal to 119. By the condition on n again, n squared is smaller than 2023 over 2 times 17, which is 59.5, and this is smaller than 8 squared. Therefore, n is equal to 1, 2, 3, up to 7. Putting these values of n into the equation, then we get the following 7 pairs of solutions of m and n. In all cases, m is not an integer, therefore there is no integer solution for case 4. At this moment, you may expect that as k is getting smaller, the range of values of n is larger, and there are more and more to try. It seems that it's not very effective. However, the consideration is different for the last 2 cases. Case 5, if k is equal to 7, then m squared plus n squared is equal to 289, which is 17 squared. Recall the Pythagorean triple that we discussed in the section of thinking process. 15 squared plus 8 squared is equal to 17 squared. Therefore, k, m, and n are 7, 15, and 8 respectively. And this is the only positive integer solution for k is equal to 7. Applied Euclid's formula again, so a is equal to k times bracket m squared minus n squared, which is 7 times 15 squared minus 8 squared, and this is equal to 1127. b is equal to 2kmn, which is 2 times 7 times 15 times 8, and this is equal to 1680. So a and b can be these 2 integers, or reverse the order. After working on 5 cases, we get a new solution to the equation. Do we have some more in case 6? Case 6, if k is equal to 1, then m squared plus n squared is equal to 2023. For the range, n squared is smaller than 2023 over 2, which is 1011.5, and this is smaller than 32 squared. Therefore, n is equal to 1, 2, 3, up to 31. So there are too many values of n to try. Instead, we consider the range of values of m. Let's write the equation in this way. 2023 is equal to m squared plus n squared. Bear in mind that n is smaller than m. Therefore, m squared plus n squared is smaller than m squared plus m squared, which is 2m squared. Divide 2 to the other side, therefore m squared is larger than 1011.5, which is larger than 31 squared. Therefore, m is larger than or equal to 32. So this is the minimum value of m. Let's find out the maximum value. Again, by the equation m squared plus n squared equals to 2023, left-hand side is obviously larger than m squared, while right-hand side 2023 is smaller than 45 squared. Indeed, 45 squared is 2025, that is 2 years later. Therefore, m is smaller than or equal to 44. Combining the 2 results, we'll have m is between 32 and 44. Still quite a lot of values of m, but much less than those of n. Put m equals to 32, 33, up to 44 into the equation, then we'll have the following pairs of solutions. In this case, none of the values of n is an integer, so there's no integer solution for case 6. To conclude, for the equation a squared plus b squared equals to 2023 squared, there are 4 positive integer solutions of a and b, as shown here. Ultimately, we have solved this Diophantine equation of 2023. I hope you enjoyed this video. please give me a like, share and subscribe my channel. I'm happy to see your views in the comment section below. That's all I have for you today. I'll see you next time in the video of number theory. Bye!